Thank you, everyone, for coming to my talk on the day in the life of a packet. I promise it won't take a whole day. I also promise that I won't tell you everything. As I was preparing this, I realized just as I went down through the levels of things that I thought that I understood, that the internet is way more complex than any one person can understand, and I'm willing to embrace that. And the other thing that I'll say going into this is, I don't really know how much people know about how the internet actually works. And so I'm willing to embarrass myself in two directions. One, by being so embarrassingly simplified that you're just going to say, well, of course it works that way. Why would you even bother to say that? But also on the other side is like, wow, I had no idea it was so unimaginably complex. And the internet that I know has been growing. It existed before I got to it, but I got to it fairly early. I started working on the internet in 1985, which is early enough that some of the things that were new to me then are not new to anyone who's ever come to it since then, because they've always been there. But also because the internet has grown in complexity and in size so much that it's, I think, gotten to the point where it's unimaginable how complex it is. So that's just a preface for things. I'll talk in the ways that startup companies, even though I'm not working at a startup right now, always talk about their incredible journey, which is to say you start somewhere and you end up somewhere else, you're not quite sure how. And how the internet works, really, I want to slow it way down to one packet at a time to start. The network that we know and the applications that we build are built on lots of layers of simpler things. Simpler things are rarely very simple if you dig into them deep enough. I won't be talking about how Wi-Fi networks work, because if you really want to talk about how Wi-Fi networks work, you need to divert into how radios work. And if you divert into how radios work, you're a multi-day conference just for that. Because it's analog technology and it's magic. And I do analog technology and magic as a hobby for ham radio, but I'm not even going to ask you to get into the details of all that. The trouble with talking about complicated networks, on the other hand, is that they rarely fit onto a single slide that you can say, wow, this whole thing is here and it's complicated. No, it's layers upon layers of complication. And it's a different kind of complication than most people dealing with software deal with, because network technologies have been built on top of older technologies for a long time. There really hasn't been a cutover date of really any importance where we say we're going to stop doing everything else, we're going to start something new. There's not that magical time where there's a brand new programming language and everyone is inventing libraries for the first time. It's much more evolutionary, layer upon layer, using the things that worked last year and making them a little bit better. And the networks, as a result, get much more complicated over time. They get more complicated because we never get a fresh piece of paper to start over with. Even the transition from IP version 4 to IP version 6 isn't really a clean sheet of paper transition, because you really want the people on the new network to still talk to people on the old network, so you have all sorts of crud going on there. And really, it's important to understand some things about how packet-based networking works, but it's completely okay not to understand everything. In the same way that if you're developing for the web, you work hard to get your work done, and there are layers above you and layers below you that you have to ignore because it's just too complex. So if I exhibit some ignorance or if I gloss over some things here, it's that I can assure you that 40 years of study is not enough, that it's messier than that. And I also want to give a different perspective on open source. So internet technologies have a lot of open source in them, but they also have a lot of proprietary stuff in them. But one of the things, especially in the internet engineering world, that happens is you get an emphasis on rough consensus and running code. So rough consensus is people pretty much agree on how things should be, but the proof of it is more than one organization can take the specifications as written, code them up, test them against each other, and see how things actually work as opposed to how things work on paper. And there was a famous series of conferences, the Interop conferences, that ran through the 80s, and I don't know if Interop is still going now, I don't think so, but it was, a decade plus worth of conferences where the game of the show was everyone bring your new equipment and we'll all plug it in next to each other and we'll see if it works. And that kind of experimental, like you can't really standardize something, you can't really call something open until more than one organization can successfully go from a specification all the way to something that's working. And so rather than just being concerned about having code being open, you work very hard to document the protocols that people use and to document not just how one thing works, but how that thing works in cooperation with, not in isolation, but together with something else. Because it's a network you're building. It's not a single monolith. And the strategy would sometimes not always observed, depending on how much market forces compromise this, but only to really standardize and agree on a protocol when multiple organizations can independently build something that works together with something else. And so the network of packets that we have floating around the world exists not because there's one packet central that controls everything. It's because there are hundreds or thousands or tens of thousands, depending on where you want to measure, of organizations cooperating to make that all work. And it's it's not as consolidated, I think, as some of the other parts of the net. So one of the things that I want to start out with is do the simplest thing that could possibly work and describe to you a day in the life of a packet from the perspective of a protocol known as ping. Not ping the duck in the children's story, but ping the very simple ICMP echo system that's out there. So how many people, and this is like a temperature test for the room, how many people have used ping before? So okay, great. How many people could say that they understand how ping works? Less. Okay. How many people in a brave moment and a week of coding could probably write ping? Okay, so we're in a good room because you'll sympathize with me to say ping is about the limit of what I think I could understand. Like if you sat me in a room with a bunch of code and some books and said you're going to start from scratch, you're going to implement this simple protocol, you're going to do the client side, you're going to do the server side, I could probably do it in a week. Even using libraries, it would be seconds, right? But you could probably start from scratch. So the way that ping works, the internet is not a circuit switch network, it's a packet switch network. So you're not like making a phone call to someone else, you're assembling a packet together and you're sending it out in the world. And the ping protocol, which was literally invented, discovered, sort of hard to say which one it is, back in 1983 by a fellow by the name of Mike Moose. He figured out that it should be possible to send a packet to a remote server and have the server take that packet, receive it, transform it back so that its source and destination address is reversed, and have the packet come back to it. And the initial implementation, he wrote the code for the client, he added some features, great, ready to go, discovered that the kernel that he was using didn't support that function because this was so early. No one had done this before. So he, all right, got to write some kernel code too. About 1,000 lines of C to do the whole thing. Why would you bother to send a packet back and forth? And the simple thing was that 1980s networking was a lot more flaky than it is today. Packets didn't always get to where they were going. You didn't quite know why. You might have a network that swallowed packets that had certain bit patterns in them because the layer separation hadn't completely been figured out. And also, sometimes your network was slow and you didn't know why. So this very simple protocol won Mike a Lifetime Achievement Award in 1993 for the construction of this thing. He sadly died in 2000 in a car crash, so we don't have the benefit of 40 years of experience of like figuring things out from that perspective. So what can go wrong? Your network might not be as fast as you think it could be, and so you have to do some performance tuning and whatnot. You might discover that you're dropping packets from time to time. The internet is a big place. You could drop packets for lots of reasons, but it's good to know that it's happening. Ping sort of tells you that something's going wrong, but it doesn't tell you very much, and I'll come to things next. Good stories about people using ping as a debugging tool for their local area network, where they set up the response and fed it into a voice-to-text, text-to-speech synthesizer, and then played the synthesizer loud and jiggled some cables until the sound stopped, so they could figure out like which particular connector was out of order. In modern networks, you'll occasionally see ping delivering packets out of order, where you get 1, 2, 3, delay, 8, 7, 6, 9, 10, 11. So you know there's some buffering going on that you might want to get something about. Or in some cases, the buffer will, if your network connection is flaky or you're on a cellular connection that's not working very well, you might get a big burst of old packets all at once coming in. So the next step beyond ping is traceroute. This gives you a little more understanding of where the packets are going in the network, not just that they're not getting there or they're getting there, but to see what the path is from here to there. I picked the simple one this morning, a simple one that hides in it some complexity that I'll get to next. This is a name server lookup, looking up a name server, quad 9, 9.9.9.9, which some people use as a name server. And discovering that from the coffee shop here, that server resolves to a system you can see in step 4 that it's 2 hops somewhere that doesn't say exactly where, and then if you read step 4 it says it's in Atlanta, or you can assume that it's in Atlanta. So the center of the internet from the perspective of this query is look to get to a highly available server, trace the hops out. And the way the traceroute works is really kind of clever. You would think that as soon as ping would be invented, you'd invent traceroute, but it took years. And what happened was, as the networks got bigger over time and more complex and more segmented, where there was more carriers between you and the end, the chance that someone in the middle that you've never heard of was having a problem and a bad day, and you needed to send a note to your network operations center to try to get a hold of their network operations center to see what was going on. So packets, as they're going through this network, have a field in the packet structure that's a time to live field, and the time to live field gets reduced by 1 every time it goes from hop to hop. And the initial design of this was such that you could prevent routing loops so that the packet would eventually exit if it spun around, if it was confused about where it should go. It would eventually get dropped. So with traceroute, the strategy is you send a packet out with a time to live of 1 and on a certain port, and you get an error message back that says this packet time to live exceeded, it didn't work. So what you know where you got that error from. So packet number 2 is, oh, well, I'll send it out with a time to live of 2 and trace it out 2, you get an error message from the second hop. It made it through the first hop okay, and then it gets the second hop. And you do that, the code for doing this does that incrementally until it finally gets to its end destination. Intermediate network hosts might drop the packet along the way because they're too busy forwarding packets in the right direction to deal with error messages. So it's a little bit lossy and a little bit like subject to interpretation. But basically, if you look at this trace, which is a simple one, you can see that most of the systems along the way, except for the first one, which didn't respond for some reason, will tell you where things are. So traceroute is super handy for visualizing how the network works, how things are plugged together. It can also be really useful if there's problems in the network, where if you have if your pings show a lot of errors or if your network connection is really slow, you can start to winnow out, like, is it me? Is it the end host? Is it somewhere in the middle? And we do this at work. I work at Equinix, which is a global infrastructure company. We ask this question all the time of our customers who, if you have a big enough customer list, eventually someone is going to complain that something is slow. We say, all right, do this MTR traceroute thing, send us the result back, we'll stare at it, and we have enough relationships with enough of the carriers in between that we can figure out if something is going wrong. And so the day in the life of a packet for something that's going wrong might be, a carrier is having a problem on a link from Singapore to Sydney, and therefore your traffic through that link will be slow because they're getting error rates that are elevated on that because some piece of optical equipment has failed or has started to fail. And that's not something that you can observe directly from your endpoint, but by sending that information upstream, you can get it into the hands of people who understand it more. Mostly it's a matter of like saying, is it me or is it you or is it somewhere in between? There's also the notion with traceroute of scenic routing. I love this phrase, I had to include it. Scenic routing is the idea that the path from you to your destination endpoint doesn't seem to take a very direct route. In particular, you run into the problem where packets, and I've seen this happen at home in Ann Arbor. Packets from Ann Arbor to New York will sometimes wander around a little bit in the suburbs of Detroit, and then they'll head to Chicago. And then they usually don't wander around very much in Chicago because I guess it's windy there or something. And then they'll head to New York. And that's largely because AT&T, the fiber network that I'm on at home, is really part of a network that's homed in Chicago, and so everything goes to Chicago to get routed. Even if, like, there's very little parts of their network that are interconnected to anyone else in Michigan. I can't explain why. It's cheaper, I guess, to centralize things as opposed to distribute them sometimes. So you get scenic routing, and sometimes this scenic routing gets really extreme because the internet is indeed a series of tubes connecting things from point to point, and sometimes things go horribly wrong. And the the historical story behind this is in 1929 there was a earthquake off the shores of Newfoundland, and it broke 28 of the telegraph cables there over the span of 13 hours because there were underwater landslides that were wiping out cables. You'll see underwater volcanoes. In Tonga, there was a volcano that blew up underwater and basically wiped out the fiber infrastructure that was connecting that island. And you'll also, in addition to natural disasters, which happen maybe I think 20% of the time in these underwater cable failures, you'll see man-made failures, typically fishing boats dragging an anchor across a cable run, and that'll pull a cable out and require that a specialized cable ship have damage. The most fun trace route that I ever saw was a trace route from, there's these systems called looking glasses that let you see what the network looks like from a different part of the world. And so you log into a looking glass and you can do a trace route from somewhere else. And so there was a fiber cut of a bunch of cables off the coast of Taiwan after an earthquake. And by looking at the looking glass in Taiwan, you could see that the bits starting from Taiwan would go all the way across the Pacific, through Atlanta, through Europe, and then back to Singapore, because that was the fast way to get there, because so much of the infrastructure had been damaged. Usually when a segment goes down, the routing protocols take care of it. If there's not a single route, right, if you're not at the very end of a network, the routing protocols will route around damage. The common routing protocol in the internet is BGP. It's simple enough to have been invented on a napkin by some very, very smart people who didn't fill out the entirety of what they were doing. So there's years and years and years of development of cooperative routing amongst carriers. So how do you handle all this traffic? You have an internet worth of people all looking to, say, look something up on a name server, right? They want to go to google.com and they want to know what address to pick for that. One way to do global infrastructure is to build a single great big server somewhere, right? You're going to build the biggest machine you can. It's going to handle the most packets. It's going to be the fastest, whatever. But it's going to be a long way away from people in a lot of places. So the next iteration of that beyond like single big server is we're going to build a lot of identical things and scatter them around the world. But then you run into the question of like, how do you pick which one is best for you? Like, how do you pick which one's closest? So the magic of this, and I started reading about Anycast because I knew that Anycast existed, but trying to plumb the depths of how clever people have been with routing protocols, really challenging to the brain, especially when you think like, how on earth are you going to debug this globally distributed system? So Anycast is the notion that, and these IP addresses, if anyone is going to memorize an IP address or spray paint it on the wall or whatnot, there are a couple of name servers around the world that use this technology called Anycast. And the basic idea is that you rely on the internet's notion that you connect to the shortest path first to get to a given address. But instead of having a single machine advertise that address, you have dozens or hundreds of machines all saying, yes, I am at this address. And you let the routing protocols sort out which one is closest so that you go to the one that's closest to you. And that was the example with the server in Atlanta that I showed in Tracer in the beginning. 9.9.9.9 is scattered throughout the world. There are dozens, hundreds, I think dozens of servers, well, no, I think it's hundreds of servers that have that IP address, that if you are close to them, the routing protocols will direct you to them. But if you're not close to one, you'll be close to something else, and you'll pick the right the right one. And you would think this might be a little bit dangerous because the right one might be this right now, but a minute later, the routes on the internet might have changed, right? It's not a static network, it's always changing. But it turns out that in practice, most of the time, the next route to a certain spot for the duration of what you need will be there. And this lets you split the load for name server requests among many cities on many continents without having the user of this system have to know very much of anything at all. It doesn't require any additional client-side software. No one has to adapt to it. It really doesn't require any additional routing infrastructure because BGP already knows how to route to the internet. So it's this extraordinarily clever. It was, again, it's hard to describe what these things, whether they were invented or they were discovered, right? There's this sense of the anycast nature of routing already existed before it was being used, and so it's just a matter of like twisting your mind a little bit to figure out how things to work. And with this, we get to the domain name system. How many people have ever had a problem with the domain name system? Okay, so again, universal, right? This is the haiku that some people have up on their wall on a big wall-sized poster when they're debugging networks. Domain name system is a incredibly powerful way of distributing a global. It's a globally distributed, decentralized database with actually pretty good consistency guarantees, which seems like basically impossible to think that someone in the 80s would have thought of that and have had it scale up to that. It's just like, who on earth would thought this up? But collectively, people did. I, again, am old enough that I remember host.txt, which was a file that included the IP address of every server on the internet. If you can imagine everything fitting in one file. And the reason that the switchover from host.txt to the domain name service happened, people were concerned that text file would get too big and that it would take up too much of the bandwidth on the internet. And they were right. So DNS addresses the question of both what is the address of a system, and then through a clever mapping also what is the name of a system. And it does so through protocols that were originally developed in the 1980s. 1987 is when the original RFCs came out. DNS came from a simpler time when you could not have an encrypted protocol and still have things work and not have to worry about encryption problems coming along the way. It also came from a simpler time when you had a choice between unreliable or UDP, unreliable datagram protocol, or TCP, transaction control protocol, which is a reliable protocol. Over time, and the numbers here on the slide are the requests for comments or the RFC numbers. RFC 1034, so there had been 1,034 requests for comments on various internet standards by the early 80s. Fast forward 15 years later, there are now 10 times as many specification documents out there that describe how this network works. Some of them are overtaken by events, some of them are informational, but the network, the internet as we know it, basically has a library of on the order now of about 10,000 documents that describe in detail enough for you to implement it how things work. So the basics are in a TCP connection, in a DNS lookup, you specify a resolver to point your query at, and you ask for, you have a query lookup that's the thing you're looking for and what type of information you're looking for coming back. So you say, you might have a question that said, give me the IP version 4 address record of allthingsopen.org. And that packet would go to a resolver that you had configured. Hopefully you configured a caching resolver so that if it had already seen that question before because you were here, someone else had asked it, that cache would contain the answer already and it could just give you the answer back. You probably also want a recursion resolver so that if it doesn't know the answer, it'll look it up for you and you don't have to do it. DNS can run over encryption, which is a good thing because it means that the packets you're going to get back are reliable, and it's the answer you're going to get back is the actual answer, not something that someone interposed out from you. So recursive name servers, as I described before, you look something up, you're asking something that has a cache, the cache already has the answer in it, you get the answer quickly. You want to point yourself at a resolver that's really busy because it'll be more likely to have the answer already there for you. And you also want to have these resolvers at a very central part of the network, because if your resolver is hundreds of milliseconds away, then every single name lookup you do is going to be really slow, and your entire internet experience is going to be really slow. And that's one of the things that I've been working with with the Quad 9 folks is planting some of their resolvers inside our network at Equinix. And we've measured reductions in average lookup times by about a third, just by having the resolver point be more central to the people that they're trying to serve, which is really neat. It's not typical that you can speed things. I mean, you're speeding things up by tens of milliseconds, right? So in the grand scheme of things, you can probably cope with tens of milliseconds, but measured out over millions of users, that's an actual pretty cool thing to be able to do. So I mentioned that the resolvers had caching. So one of the problems of DNS, if you've ever had a problem with DNS, is that sometimes it gives you the wrong answer and you're not quite sure why. And the reason, generally speaking, that you get the wrong answer is that some data has changed and the network hasn't caught up to the fact that it's changed yet. Just like packets have a time to live field, DNS records have a time to live field where they'll say, the address of allthingsopen.org is such and such, and I promise that that will be true for the next hour. And so the server that has the cache can say, oh, that authoritative server has promised me something for an hour. I can keep it in my cache for an hour and give that out as the right answer for the next hour and not have to look it up again because I have it on good authority that it's going to be true. So you have these caches building up with stuff. Well, what if for whatever reason you need to change the IP address of a host? And the answer there is, well, if you plan carefully, you can reduce the time to live value in your server record to say, well, my address is here, but it's only good for the next 60 seconds. And then 60 seconds later, it would ask again what the thing is. And so if you can manage to hold your system together in such a way, you can avoid having a cache give you the wrong answers quickly. And then finally, I don't know if anyone has seen this quote, you're not expected to understand this. This is a quote from the kernel in the 6th edition kernel, which is even by, I think this is from the 1970s, some particularly obscure, arcane version of things. As I think about complexity, so the systems that I got started with were slow, they were unreliable, and the tools that came with that didn't always give you the right answers, but they were developed in concert with the network as it was. And so as systems get older, they accumulate more features, right, if they're still useful. So ping that I described at the beginning is, by inspection here, pretty much universally known. People kind of understand it. They kind of know what they're getting. Traceroute, I still have to explain traceroute to people because it's not as familiar. Anycast is something approaching black magic, but sort of good magic, because if I were in the position of needing to operate a Anycast network, the question was like, how can you know that it's working? Which is like an impossible thing to know. And then DNS has a whole industry around it, and it has been evolving. You saw those RFCs from within the last 2 years, people still defining how this thing works. So the complexity builds up over time. And just to give you a timing on these things again, right? These are all, ping, traceroute, Anycast, and DNS are all from the early to late 1980s. And they've just been getting messier and harder to understand for the most part ever since. People can only people can only cope with so much complexity. And the hardest part of pitching this talk and putting this in is like, how much complexity is there in your world, and how much have you been able to successfully ignore all the complexity in someone else's world because you don't have to worry about it. I think with home networks, people have been forced in some way to deal with some of these things because they don't have an IT department and things don't work, and cable companies are not perfect and phone companies are not perfect. But if you're actually trying to get a problem solved, you might not even know or care where your packets go as long as they get there on time. And you may or may not be the person in charge. You're probably not the person in charge of making it work. And the details that as an operator of a network or a manager of a network that you can see are often hidden from the outside. So I'll end with this wonderful, wonderful quote from Ellen Ullman. She's written about technology development. She says, "We build our computers the way we build our cities, over time, without a plan, on top of ruins." And that's kind of simultaneously horrifying and comforting. So I'll leave it with you with that. Thank you. The cue for thunderous applause.